So here comes to our second talk, Professor Wenfei Wu from Peking University. Wenfei has been working on in-network computing for many things.
Yes, quite a while.
For many years.
Yes.
Right. So he will be talking about how to build the ecosystem for ISC.
Yes. So good morning, everyone. So I'm very happy to talk again here in APNet. This is the third time I talk about in-network computing. So today I want to talk about how in-network computing, or INC for short, how it matures from research prototypes to protocol. So and hopefully to an ecosystem that the whole industry can build on. Oh. So large model training, inference, and big data analytics all run on a cluster scale today. And at this scale, data exchange is no longer a negligible part of the job time. Look at the trend. So the flops requirement grows about 750 times every 2 years. It's much faster than network capacity. So the result is that on the right side, so expensive GPUs sitting idle waiting for the network. So the good news is that these clusters are now in a single administrative domain. Unlike the internet, we are free to deploy programmable data plans to customize the stack end to end. This opens the door to INC, which is defined as offloading application functions to network devices. In this talk, I mean switches. The next device is switch. So why does this help? There are 4 reasons. So if we apply INC, we carry computation result instead of raw data. So traffic volume drops. And second, we reply a request at the middle of the path, so fewer transmission hops. And computation and communication are pipelined at the packet level. One packet is in transmission, another is in computation. There is a time overlapping. And we also free the host CPU or GPUs for network stack cost. But if we take this INC seriously as a research field, this definition is not very, I think it's vague. I think we need to answer 3 fundamental questions if we treat this as a research field. So first, what is the function and the computation that we should offload? Is border. And what switch hardware architectures support that computation? And the third one is how do we develop these functions on this architecture? So this sounds familiar because in programmable data plan, they answer these 3 questions. So programmable data plan offload network function, use PISA architecture, and they use P4 language. INC target application functions. So we need to rethink these questions. So we are still exploring this answer. I don't have a clear answer now. At the end of this talk, I would give some intuition. So today I'm going to share more use cases, more concrete use cases. So back to APNet 21, I present our first case. Offloading or reduce in multi-tenant clusters. So the ATP work. Back then, the future work was listed as we want more INC applications. We want resource management for INC systems, and we need to verify INC protocols. Then 2 years later, in APNet 23, some boxes got filled. We offload other applications, both AllReduce and reduce by K in data analytics. On management, we have job replacement. we have job placement and runtime resource scheduling. So the future work then was pointed at the remaining flags. We still want more applications to show its promise, and we need to study the device itself. Today in 26, I'm here to fill in a few more. That is the path we have taken. I have been reporting it to this community chapter by chapter. Today has two parts. Part one is the effort we need from device vendors. That is the ecosystem story, Epic. Part two is a new ink use case for long context inference, Turbo. Before I introduce these two works, let me quickly review the background. IInc empowered AllReduce. Model training iterates, so workers in distributed data parallel training, workers compute gradients, and these gradients need to be aggregated and sent back for model update. So the operation to sum vectors across machines and return the result to all is called AllReduce. It's everywhere in AI and the HPC, also in tensor parallelism. So non-ink solutions or host-centric solutions have no cost. So we can apply a parameter server, concentrate all traffic at one point to perform this operation. So it has a bottleneck. And we can also apply ring or reduce to spread the load, but it takes too long to transmit the intermediate states. It doubles the traffic volume. Both leave performance gaps. The ink design need just the two data structure. The worker chunks its gradient into a packet sequence and stream it into a sliding window. We assume the window size is W. The switch organizes its SRAM as an array of N aggregators. So the workflow is as follows. The worker keeps sending packet within the window. The switch addresses each packet to an aggregator by its sequence number. So here we can use a modular operation. Packet sequence number modulo the array size. So we achieve this addressing. When aggregator completes, the switch multicast the ACK back that page back the result. ACK advances the window on the end host and the new packet flows. So let me show the animation. There are two workers with window size 2 and two aggregators. So packet 0 and 1 arrives at the switch. The switch accumulates them in the aggregator 0 and 1. When both workers 0 arrive, so the switch completed the aggregation and send the result 0 back. This ACK packet would advance the window, so the worker would send a new packet. So this workflow continues until the end of the packet sequence. So the real system also need to handle more things. We need to handle packet loss and switch memory recycling, congestion control, and floating point operation support. So I would not go into detail here. So we implemented this protocol and test it on 4 GPU test bed. Compare it with Nico. So we can achieve performance gain. We run Nico test on AllReduce. We can achieve performance gain about 40%. The theoretical upper bound is 100%. And around this mechanism, a body of management work has grown. So because each job needs to use some resource, switch memory in the switch. So how do we manage this resource to many jobs? This is a management problem. So there are a few problems. How do we place jobs considering the ink resource? And if two jobs share the resource, how do we multiplex the resource at the runtime? There are a series of works about this. So now we arrive at the harder question. Since with these mechanisms ready since 2023, we have been trying to persuade vendors to adopt INC to add this feature on the switch. We expect to reshape the ecosystem from the internet layered architecture to a holistic one for AI networks, where this new kind of infrastructure vendor span host and network devices. So this brings us the core for this talk, the enabling in-network collective communication on Ethernet and the EPIC system, which is a CCOM paper this year. So our initial vision assumed that cross-layer construction for performance. The reality is that a vendor capable of handling every layer, host, NIC, switch, libraries, barely exists. The only example we see international vendors are NVIDIA, but most vendors do not cross these many layers. So this path is not very feasible. Very few vendors can do this. Are doing this cross-layer thing. Vendors meet with two problems. First, INC is inherently cross-layer, collective library, protocol stack, NIC, switch, controller. But Ethernet is an open ecosystem. Each of those is a separate eco niche in a functional scope with its own players. For a single party, there are three concerns. It cannot build the whole system alone, so it cannot capture the game. Even a single party implement this function, it cannot achieve the game. Second, adding functions in its own scope is expensive, and the resulting poor return ROI, return on investment, deters the vendor from committing resources. The second problem is switch vendors differ. First type 1 vendors, they may have technologies of both switch and Rocky NICs, RDMA NICs. Type 2 vendors may only build switches. So any INC design that requires Rocky stack would automatically exclude type 2 vendors. So they simply cannot follow type 1 vendors' technical approach. So a standard that only half the market can implement is not a standard. So our answer here is one principle here. We need to define unified abstraction and polymorphic realization to implement INC. So the unified abstraction defines the standard interface between eco niches. So it can break the upstream and downstream vendor lock-in. So polymorphic realization means each functional scope admits multiple vendors with different capabilities, which lowers the investment each one must make. So abstraction fixes the boundary, realization follows the capability. Here is the picture shows the abstraction. So when we do in-network collectives, the leaf nodes we use a tree structure. This is a logical tree. Leaf nodes are hosts. The intermediate nodes are switches. We map this tree into the cluster. And each edge has two endpoints. We associate an RDMA endpoint, is QP, with the edge endpoint. And also we associate an endpoint to a switch or host NIC port. Then concretely, when we preserve the standard interfaces between functional scope. So this is the host, this is the switch, and this is the cluster manager. So on the host, we define the interface clearly for following the current standard. So the training program speaks collectives. The communication library speaks RDMA verbs. And the Rocky stack speaks packet IO. Yeah. So every every row, every player, switch vendor, and class operator stay within their familiar boundary. So now let me introduce the three polymorphic modes to design the switch. Mode 1, we call it connection terminated. Is suitable for vendors who own both switch and the rocket RDMA technology, like NVIDIA. The switch ink engine simply reuse rocket. So rocket assembles packet. Assemble packets as messages. So and the ink engine would operate on the message to perform the reduction and replication on messages. Then rocket send them back as packet. It's just like we put a parameter server on the switch. Yeah, this picture shows the workflow. The data goes along this tree, and the result is multicast back. Mode 2, connection translated, is suitable for vendor with ordinary switch, with ordinary Ethernet switches and no RDMA expertise. It's a minimalist pipeline. So a packet is checked with its deduplication, and the data is aggregated, and it is on the return trip. It's replicated, and it's sent back. So this is the minimal list function we need to add this function. Note that we don't put the whole RDMA stack on the switch. We put these modules on the switch, but we need to ensure that the interaction with the RDMA NIC is correct. The interoperability should be correct. Let me show this workflow. So here, assume all these packet zeros from 4 machines are sent. They are aggregated along this tree. Okay, these are with RDMA RC connection. Then the result is sent back. So this result data packet would trigger an ASIC. So because this NIC would think some data packet comes and it replies ASIC. So this ASIC would acknowledge is the red packet, and we have the switch to reflect the ASIC back to the host, to the NIC. So this ASIC reflected ASIC would acknowledge the very first packet. So the switch can, without RDMA stack, the switch can still interoperate with the NIC correctly. So mode 3, we call it connection enhanced. It sits in between. It adds 2 functions, per hop ASIC and retransmission for vendor evolving toward switch plus RDMA. This is a middle ground. Yeah. Okay, we add new modules. Yeah, we make a hop by hop reliability. So and crucially, these are not silos. Vendor can evolve from simple to complex modes over product generations. These 3 workflows, they share the same skeleton. They use the same set of modules by design. How do the modes compare? All 3 are proven correct by model checking, and mode 1 plays in transmission efficiency. Pays in transmission efficiency because mode 1 is RDMA. It operates on messages. It's coarser granularity. Mode 2 is simple. Mode 2 is simple, but it needs a large buffer. It needs a pass scale buffer and a global synchronization, so it pays the loss tolerance and space simplicity. Mode 3 balances is something in between. The radar chart shows their advantages. Avatar is better. And this involution is not so we can support 2 kinds of vendor. Top vendor can evolve from mode 1, then cut some function and evolve to mode 3. It's here. So go this path. And the non-top vendors, they can go from mode 2 to mode 3. From the simple to the complex. So what does polymorphism buy us? Every vendor can implement INC. We can break the vendor lock-in, and every vendor can start from simple to start simple and evolve rapidly deliver with low investment risk and best arrive at the best performance in the long run. So to push adoption, we release in network collective specification. We validate everything each party cares about. We want all parties to agree with this feature. So we evaluate its correctness. We show its acceleration, interoperability with Rocky, and evolvability, resource manageability, loss tolerance, and chip feasibility. So we show some highlight result. So we on Tofino we implement this version. If we also use switch ML and ATP as baseline. So first, INC solutions outperform non-INC. So Epic switch ML is better than can beat Nico. And second, Epic can saturate bandwidth with lower CPU usage, because its transmission is hardware offloaded through Rocky. ATP and switch ML are built on RDMA, not RDMA, DPDK. And also with communication accelerated, we can also accelerate the end-to-end performance of training and inference. So one more thing here, we build a protocol verification tool. It's a model checker, which complement the future work in 2021, at least here. So when we design protocols, we need to make sure the design is correct. So we need a protocol verification to prevent bad things from happening. So now the second part is another INC use case. Context parallelism. It's also called a sequence parallelism. Long context applications are everywhere, from RAG, long document understanding, and multi-turn dialogue memory. Long context inflates three things: KV cache memory, attention computation, and inter-GPU communication. CP split sequence across GPUs and share KV caches via communication. This is the turbo work also in CCOM this year. So quick mask cap. So we have in the decoding phase, we have token 1 to S. Each token is transformed to K and V, to K and value. So we have a K and a K sequence and a V sequence. Token ends query is also transformed. So we compute the attention using this the query and all the historical KV caches. Use this equation. Then we generate the next token. And existing in context the parallel. So the sequences are on different GPUs. We assume this master GPU is computing the next token. So there are two approaches to compute. First, this master GPU fetch all the KV locally, then perform the computation. Use the queue to compute the attention. Another approach is we can broadcast this queue to other GPUs. Each GPU uses its local KV and this queue query to compute the partial attention. Then the master GPU fetch all the partial attention and merge them as the attention. The first approach has incurs high communication volume. The second one would incurs incast and reduce the bottlenecks. There is a one-to-many and many-to-one traffic pattern. So it's natural to use INC to solve this problem, because when we use pass queue, we pass the queue to all the GPUs. When we send broadcast queue, we can use switch to do this broadcast. And when on the return trip, when partial attention are fetched, they can be aggregated in the switch. So we solve the communication bottleneck. So the difference is that it's not the partial adaptation are not simply summed up. It's a weighted summation. So each partial addition is accompanied with a weight. So we need to compute this weighted attention. So we can do this pairwise because these attentions arrives at the switch one by one. So we compute one by one. So we maintain this average attention and the weight. And for each incoming attention and weight, we use this formula to update. We can get the same result as this equation. There are some PISA-specific challenges. First is switch programmability limitation. We cannot perform exponentiation and division. So we cannot compute this weight and multiplication and division. So how do we do that? We pre-compute a lookup table. Use A. We enumerate all the possible A bar, W bar, and AI, WI, and pre-compute the result. So the computation becomes a table lookup. To compress the table size, we quantize the attention as int, and we also use a log W to represent W. We can reduce the range. And the second challenge is the memory access limitation. So each pipeline stage can only allow the one read and one write. So after we perform this computation, we cannot write the result back. So if packet 1 performs the computation, we store it in the later stage, and the second packet would complete the computation and store it in the later stage. So we need to roll forward the state as we compute on the pipeline. If we arrive at the end of the pipeline, we recirculate to the beginning. So we tested on the 4-node RTX 3090 GPUs, and we test Llama and GPT-3. Llama, and we use simulation to evaluate its performance in GPT-3. So in the test bed result is that Turbo can achieve better performance, So lower is better here, up to 37%. Here the baseline is PassKV because the default engine like VLM and SGLang, they do not implement PassQ right now. And in the large scale simulation, we compare across PassKV and PassQ. Turbo reduces master traffic and also while maintaining the lower TPOT. Finally, the conclusion. So the roadmap is updated. At the bottom, we want the device to raise the performance setting. And in the middle, we want the communication layer to enable easier deployment. And in the application domain, we want support more applications. And also, we need a runtime management system for the cluster. And for development, we need tools to make sure the protocol is correct. 3 takeaways. Years of effort have shown INC is not only promising, it's more and more practical for distributed system acceleration. And Epic let a fragmented Ethernet ecosystem build cross-layer systems with unified abstraction and polymorphic realization. Turbo opens a new use case, context parallel, with new scaling reduce primitive that overcome the switch limitation. And look forward. In the short term, I think the existing case should be deployed and with better management policies. And we still need to discover more use cases. A very important thing is switch macro architecture design. We need to add this new functionality. In the long term, the vision is simple. We want to make the network a new accelerator for distributed applications. It's like a GPU is the accelerator for servers. We need the accelerators for distributed applications. And the 3 fundamental questions written down. Here, these are open questions. I have some intuition, which I would explore in the future. So what functions is suitable to use INC? I think it's stream processing. So data unit comes in a stream is processed one by one with some locality. What architecture is suitable for this processing is, I think, pipeline is better. It's not a many core architecture, because many core architecture has a shared memory bottleneck, I think. And for development, maybe we can extend P4 or some functional programming. Yeah, these are open questions. That's all we have. Thank you. I'm happy for questions.
Yes. Here we have time for one question.
So here we have this line of work. Two sort of broad questions around the ecosystem and the overall principled way to distribute functionality between switch, smart NIC, host. So do you have thoughts on beyond the application that you've talked about? What is a good way to split the functionality such that your ecosystem questions are also answered? In the sense that some of the things that you discussed will likely cause the switch cost to go up significantly.
Yeah.
Right? So you're moving the cost from one place to another.
Yeah.
So how are you rationalizing some of these choices, especially with your ecosystem questions? And then one sort of quick question related to the ecosystem is if you've looked at the ultra-Ethernet consortium, which is also looking at accelerating, particularly AI applications.
Yeah, so yeah, we are moving functions in different places. So there must some vendor must pay for that. So if we are vendor neutral, so I think we should list all the possibilities and try to find a unified abstraction to allow all of them to implement. So and also in Ultra Ethernet, in UEC, I feel maybe AMD and Broadcom, they are dominating that. They are top vendors. They own RDMA, they own switch, so they can give us solution with these two technologies. But that would hurt the smaller switch vendors. They cannot build RDMA. So that's why I think we should equalize the vendors.
I have two very quick questions. First one is, you and I the set point to using the technical communication as a case for a event. But you just mentioned that all reduce about the others.
Oh,
there's a bunch of track communication plans.
Yeah.
Say this is my first question. Maybe you can answer that and I can speak myself.
Yeah, so I think collectives like broadcast reduce, we can apply that. But for these two, we reduce traffic volume. We don't reduce the completion time. So we can get reduce. So to get a performance gain with broadcast and reduce or altogether and reduce scatter, we need a scheduling to overlap these two collectives, these two kind of collectives. And I think in collective communication, these are, so I introduced another one, scaling reduce. And there are some attention I paid on MOE, token dispatch and combine. It's a similar issue. So one side ink or ink empowered dispatch cannot beat ordinary dispatch in terms of the completion time. But we still use ink to improve dispatch and combine. Then we schedule them when we write the program. We schedule to get the performance gain.
The second really is suggestion is how you think about more focus. I see more focus on the scale up. It's super power and the super computers and especially on computing probably they are more controlled by a single vendor, and they have more kind of application values and more money is put into that. So it's easier to put the users there instead of Ethernet generally.
Yeah. So for scale-up network, its feature, its characteristic is memory symmetric, and I think it does not have more complex flow control congestion control. This is its feature. But I think from in principle, it's not contradictory to apply in scale-up domain. The problem, all the design, I think it can be applied. But the problem is the scale-up transmission protocol does not converge. So in scale-out, all parties agree we can use Rocky. So we use Rocky to encode the ink semantic. It's very natural. But for scale-up, we either we bide with one specific vendor or we wait for vendors to converge their opinion.
Yeah, let's talk offline. And I try to squeeze time, but the talks are too informative. So
Thank you.
yeah, one thing I feel like papers is your INC. We can talk to him tea break lunchtime. Okay, let's move on. Essential speaker.